Hello, and welcome to this SRC Learning Essentials series video about the Layer 2 forwarding database. If you are not familiar with the Service Routing Certification Program, you can learn more by visiting our website at www.networks.nokia.com/src. In the following presentation, we will first explain the default flooding behavior of a VPLS and describe how the Layer 2 forwarding database is populated throughout this process. Once that is completed, we will move to the lab environment to test these behaviors and verify the FDB of a basic VPLS. Because a VPLS is a multi-point Layer 2 service, any traffic entering the VPLS must be appropriately replicated to the other locations. To help with that process, each PE dynamically builds its forwarding database, or FDB, based on the source MAC address in traffic offered to the service. Now, the VPLS forwarding behavior acts differently based on the type of traffic sent within the service. So let's move forward and look at these scenarios in more detail. First, we will discuss known unicast traffic, which is sent only to the required destination. In the diagram, PE4 contains the highlighted FDB entry, which matches customer site number 2. The figure shows an Ethernet frame arriving at PE4. The FDB on PE4 contains the destination MAC address of the frame and thus only forwards the encapsulated frame along the SDP connected to PE3. So again, because the frame is known unicast traffic, it is only sent to the required destination and not to the other VPLS sites. Next, we have broadcast unknown unicast or multicast traffic, which in a fully meshed VPLS such as this one is flooded to all remote PEs and local SAPs in the service. In the diagram, an Ethernet frame arrives at PE4. However, this time, the destination MAC address is unknown to the VPLS. Because the MAC address does not exist in PE4's FDB, the router floods the frame to all remote PEs in the service. So, now that we understand the default VPLS flooding behavior, it's time to see how this affects the creation of each individual PE's FDB. In the figure, CE2 transmits a unicast frame destined to CE1 that is received at the SAP on PE2. PE2 learns the location of CE2 on the SAP from the source address in the received frame and updates its FDB with CE2's MAC address. Because CE1's address is unknown to PE2, the frame is flooded on both SDPs in the service. PE1 and PE3 both receive the frame and learn that the location of CE2 is on the SDP to PE2. This, of course, leads to PE1 and PE3 updating their FDBs with CE2's MAC address. Since at this point the destination address of CE1 is unknown to PE1 and PE3, they both flood the frame out their local SAPs, where it finally arrives successfully at CE1. Next, CE1 transmits a frame with CE2 as the destination, which arrives at the SAP on PE1. PE1 learns the location of CE1 from the source address in the frame and updates its FDB. This time, the PE router has the MAC address of the destination in its FDB and therefore knows to transmit the frame only on the SDP to PE2. PE2 then learns the location of CE1 from the source address in the frame and updates its FDB. Also, because PE2 has the MAC address for the destination CE2, the frame is transmitted out the local SAP. So, in addition to MAC learning, it is also important to know about MAC aging. when an entry is added to an FDB, it is first given an age of 0, and each time a PE receives a packet that matches the entry, the age time is reset. However, if the traffic flow were to stop, the age would increase, and if it reaches a value greater than the age timer, that entry is then removed. Okay, so next we will move to our lab environment. There we will have VPLS 100 configured on the PE routers and is fully meshed. By running pings between the CE routers, we will be able to verify the creation of each PE router's FDB. Okay, before we send traffic through VPLS 100, we can verify that the individual FDBs are initially empty. On PE1, we can run show service ID 100 FDB detail. And from the output, we can easily see the FDB does not contain any entries. To save time, I have already run this command on PEs 2 to 4. And as you can see, they also have an empty FDB. Now, let's head over to CE1 and run ping 192.168.1.2, which is the IP address of CE2. And as expected, the ping succeeds. Next, let's view the ARP table by running show router ARP. Notice the table contains entries for the CE devices only. This is logical because the CE devices are not aware of any details of the service provider's network. Rather, the devices appear to be directly connected by a single Ethernet switch. Moving over to PE1, let's view the FDB, where we should see a total of 2 entries. Running show service ID 100 FDB detail again confirms this FDB contains 1 entry for each CE device. PE1 knows that it can reach CE1 through the local SAP and CE2 through the SDP. Over on PE2, we can run the same command. However, this time, the SDP is used for CE1, and the local SAP is used for CE2. Okay, so let's now go and check the FDBs of the remaining PE routers, where we should see a single entry for CE1. Here on PE3, we can run show service FDB-MAC, which is another command that can be used to view FDB entries. And as expected, we only see a value for CE1 with the source identifier of the SDP to PE1. And over on PE4, we see the same results. So of course, the question here is, why do PE3 and PE4 not have an entry for CE2 in its FDB? Well, when CE1 pings CE2, it first sends an ARP request to learn the destination MAC address to use in the Ethernet frame. This ARP request has a broadcast destination MAC address, so PE1 floods it to all other connected PE routers in the service, who then install the location of CE1 in its FDB. Next, when CE2 responds to the ARP message, PE2 receives the frame and checks its FDB for CE1. It finds a matching entry and therefore only sends it along the SDP connected to PE1. So PE3 and PE4 never receive a frame which includes CE2's location. And that about does it for this example on the Layer 2 forwarding database. Thanks for watching, and see you next time. Content for this video was adapted from the Nokia Services Architecture course. You can access the complete course via any of the 3 learning formats shown on this page, as well as get remote private access to a Service Router lab to complete the course lab exercises. If you are interested in obtaining an SRC certification, this table identifies the recommended courses and required exams for each of the 5 available certifications in the program.